think this is a kind of a follow-up to the DIA day. I think yesterday was like all DIA data day. What people often ask us though is how do we actually do this? I've got a mass spectrometer, but there's like all these settings and all these stuff too. What are the practical things? Why did you kind of choose these sorts of mass ranges and conditions and setups and some of it was just guessing, random guessing. Other stuff became, they're sort of a little bit educated guesses, I guess.
Fake it till you make it.
Fake it till, but that's the truth, right? There's too many things to try all possible things. So I think what Jared is trying to do is get across a little bit of how we kind of decided to guess in this correct way, and then show you a little bit of the practical things of thinking about setting up these methods.
Okay, thanks, Mike. So I'm going to try to spend about 45 minutes talking about the fundamentals of the method design. And what I'm going to do is, as Mike said, I'm going to take you guys sort of through all of the nitty-gritty steps and the reasoning and try to point out some of the caveats in DIA and these methods that we've developed. The method that I'm going to show you is what it will be applicable to a Q-Exactive series instrument. That's what we have in the lab. There's plenty of people here who can speak on how to do this for a Q-Top as well. And I can also try to help you guys. Please interrupt with questions. This is definitely designed to be a heavily interactive talk. And this is my email, so I think a few people have asked me for this. So it's Egertson@uw.edu. If you want, just go ahead and send me any emails. If you have any complaints or issues, just email Austin Keller. He's sitting in the back. His email is atkeller@uw.edu. If it's a hard question, make sure he gets it. All right. So thinking about fundamental method design for DIA. So I don't think there's really a universal DIA method. We're still not to the point where I can just tell you should always use this particular DIA method. So while I'm telling you our starting point for most things, just keep in mind that there's a lot of variables in these methods, and depending on your time constraints or the amount of instrument time you have, the amount of injections you can do with your sample, the complexity of your sample, these sorts of parameters might change. But the parameters that I want to talk about in particular that are really meaningful are cycle time, the number of injections, so the number of LCMS-MS runs you're going to do per sample, the mass to charge range that you cover in your DIA method, the isolation width, which I know we talked about a lot, the resolving power or resolution of your acquisition, and the AGC target or maximum inject time. This is Orbitrap specific, but on a top this would be dwell time or signal averaging time. So really key is cycle time. So I tend to start with thinking about microchromatography. So this is applicable to an SRM or PRM method as well. You always need to consider how wide is your LCMS-MS peak. Anytime you're doing area under the curve quant for MS-MS, you want to have at least 7 points measured across that peak. So considering a method on, say, the original Q-Exactive, let's say it's scanning at 10 Hertz. If it's scanning at 10 Hertz and we're measuring 20 MZ windows, that means we're cycling through every 2 seconds, right? So on any given chromatographic peak, you're going to measure 15 scans across that peak if it's 30 seconds wide. And of course, if it's down to 15 seconds, you still get 7 points across the peak. One thing that you could imagine trying to do, as we've talked about how the wide isolation window makes the spectrum more complex and the data more noisy, you might think about trying to do 40 10M/Z windows. For a 30-second peak, you would be just okay, right? Your cycle time would be 4 seconds and you'd be borderline. We don't do this in our lab though, because we do have some peaks that end up being narrower. But if you could even like detune your chromatography and run a method like this if you wanted to. I wouldn't recommend that though. If you have UPLC or really narrow peak widths, it gets even more challenging. So here, if you've got a peak that's 6 seconds wide, even with a 2-second cycle time, you're still undersampling that peak. So then you might start to need to consider, well, maybe I'll do 10 40 MZ wide isolation windows, right? Because then your scan cycle is only 10 scans, you're scanning at 10 Hertz, and you're sampling that peak every second. Number of injections is also a way around this. So let's say that you have a really precious sample and you want to be able to dig really deep into it. Yesterday we were talking about how the number of detections you can make in a sample increases rapidly with decreasing isolation window width. So a consideration a lot of people have is they say, well, I have enough sample, I have enough instrument time, I can make multiple LCM SMS runs on this sample. So if you tried to do something like do 5 MZ wide isolation windows in a single run, you would be grossly undersampling your peak. But if you're willing to do multiple injections, like for example, do one LCMS MSMS run covering 500 to 700 with these 45 MZ wide windows, and then another one for the rest of the range, then you're effectively sampling every peak enough, because each individual run is still going to have a cycle time of 2 seconds. Does that make sense? Does anybody have any questions? So this is a question I get a lot. So covering 500 and 900 M over Z, why not cover something wider? Can anybody give an argument for why I would want to cover a wider mass to charge range? It's not a trick question. Right. So yeah, modified peptides, more peptides. Why do you think that I keep it to 500 and 900? Why wouldn't I just go out to 1400? Mm-hmm.
And you don't have to spend time on the range where you have less things that just get less points.
That's right. Less points across the peak, or you're going to start making, you're going to start acquiring slightly lower quality data basically as you move that window further and further out. Our lab does tend to sample a narrower range. I would say it's a lot more popular to do like 400 to 1,000. But this is the decision we've made for a lot of proteins. We can still get 1 or 2 unique peptides, and for those peptides that we do measure, we get very good quant. Isolation window width, we've already talked about this a lot, but just to put it in perspective, DDA methods might have a 2 MZ isolation, DIA might have a 10 or a 20 MZ isolation width. As you increase that width, more peptides are co-fragmented, your spectra are more complex, and you're going to have more interference chromatographically. Here's what that actually looks like. So here's just an example spectrum. This is a DDA spectrum for this peptide, isolated with a 2 MZ window. So you can see that the peptide of interest is the primary analyte in this MSMS spectrum. But as the window increases, you can see more and more background interference. So I'm just highlighting the B and Y ion series, but I think this really drives it home that once you're up to 20 MZ wide isolation windows, the analyte that you're looking at may not be the primary contributor to that spectrum. What does this look like on the chromatographic timescale? So in DIA, I've always talked about doing these sort of peptide-centric targeted analysis rather than spectrum-centric, where you're trying to interpret a given spectrum. So obviously this also affects you looking at things chromatographically. So here's that same peptide that I was showing the spectra for. Now we're just showing it across retention time. And you can see the fragment ion traces with a 10 MZ window, but then you open it up to 20. So what's happening here in the 20? Yeah, something's eluding pretty close. And what else? That's right, the fragmentation, it shares a lot of fragment ions, and it's also it shares multiple fragment ions. So it could be this sort of case where I'm pretty sure this is a trace for all the Y ions. So what could be happening is it could share, for example, a suffix with this peptide, and if it's co-isolated in the window, you're going to get these really similar traces. In this case, right, the other analyte's just outside the 10 MZ and it's in the 20 MZ. This is another example of the same thing. We already talked about this before when we had the co-isolated oxidized methionine. It's the same concept. This is showing a particular case where I was looking at this peptide with a 10 MZ isolation window and then with a 20 MZ isolation window. And, oh man, it doesn't show great here, but you can see there's actually this big interference in the 20 MZ window. And when you zoom in, what's kind of, I think, telling about this interference is no amount of fragment ion resolving power is going to resolve this interference. It's like the exact same M over Z. It's actually, this is showing the trace in the interfering region. So this is showing the trace just outside where there's interference, and you look at the peak, and this is Skyline showing you where it should be theoretically, and it's right in the center of that window. It's a singly charged analyte, and we're actually querying for a doubly charged fragment ion here. But that's just to demonstrate there will be times where no amount of fragment ion resolving power will overcome your issues with selectivity, with precursor selectivity. And this is what the opposite looks like. So here I'm showing a particular fragment ion trace where the resolving power does improve your ability to resolve the interference. So this is a measurement of this B5 fragment ion at 17,500 resolving power, and you can see that it's kind of shifted, the mass accuracy is off, it's not quite in the window, but it's still integrated. But here, the peaks are actually partially resolved at the higher resolving power, and you get a clean trace. So there are some particular peptides where improved fragment ion resolving power is going to resolve a given interference, but there are some where you need to improve the precursor selectivity. So then the next question is that when thinking about these methods is, well, should I focus on improving precursor selectivity, or should I focus on improving fragment ion resolving power? And here's an example that kind of tried to answer that question. This is a paper from Bruno Demond's group where they looked at, I believe this was in a urine sample matrix, and they said how many transitions with interferences do we see in a DIA method for various combinations of resolving power of the fragment ions and isolation window width, right? So one thing you can see is at sort of the really wide isolation window width, you certainly have a lot of interferences, and then you drop down this way. So this is kind of a no-brainer. Improving your precursor selectivity gives you less and less interferences. And also, if you look at it coming out of the board, increasing your fragment ion resolving power gives you more and more selectivity. We tend to try to be in this region on our instrumentation at least 20 MZ or better. Precursor selectivity, because you can kind of see there's a big jump going from 16 to 24. And typically on our modern instruments, we're acquiring around 30,000 resolving power for DIA data. Does this slide make sense to people? Does anybody have questions about it? Okay. And also consider one big caveat I like to point out is a lot of people would be using sometimes isotopically labeled standard peptides. I know that's a common approach. And you have to be careful with it if you're using DIA. You need to really consider how is your standard labeled. So in this particular case, if you've got a C-terminally labeled standard, a heavy precursor, and then these two things get co-isolated, you're going to be in a lot of trouble if you're trying to quant with the Y ions. So what would happen, for example, is here's a peptide where the heavy standard's here and then the light one's here. They're 5M over Z apart. And then with SRM, it doesn't matter. You can use quant with the B or Y ions for this particular peptide, right? Because they're not going to be co-isolated. But if you start doing DIA with 20 MZ wide windows, and then you use only the Y ions, they're all going to have the same mass to charge. They're not going to be, or sorry, if you use the B ions, they're all going to have the same mass to charge. They're not going to include the modification. So be careful about that if you're doing DIA experiments. There will be some cases, even in a DIA method, where here they're co-isolated, but you might be lucky, right? And they might be split in different windows, so you may be okay in some cases. But generally, if you're using these heavy standards, I would just say, especially if you're doing HCD fragmentation, just use the Y ion series only. So the AGC target and maximum injection time is another thing we're going to talk about. The considerations, I think, for DIA are a little bit different than when you think about it for DDA. So conceptually, with your MSMS scans that you're doing from DDA, typically your goal of that MSMS scan is to generate an identification. And once you've generated an identification, you want to move on and get more identifications. So if you have to slow down the instrument by having your fill times be really high and filling the Orbitrap, you'll get higher quality spectra, but you don't want them to be too high quality because you want it to be just good enough to get an ID. Whereas for DIA, you're doing all of your quant from these MSMS scans, so it's critical that in the case of a trapping instrument, that the Orbitrap be filled. Those need to be high quality MSMS spectra because you're doing quant from them. Similarly, it's the same idea as with SRM. It's like a higher dwell time gives you better quantitation, and on a top instrument, you're going to want a signal average for longer. Right, okay. So all of these parameters I've covered, I haven't told you any specifics really yet. All of these parameters kind of influence each other, right? So you can say, okay, cycle time and number of injections are related. If you cover a wider mass to charge range, you might scan slower. I think I've already kind of driven that home. So the question is, how do you put all of this together into an actual DIA method that you can walk out of here and use? This is sort of the approach that I usually take. So I start with figuring out what's the cycle time that I need to hit based on the LC. How many injections am I willing to do per sample? what mass to charge range do I want to cover? And once I have that, the rest of this kind of falls out, and I'll explain that in a second. So starting from the top. Again, I've already talked about this, but figure out what's your peak width. So if you have a 15-second peak and you need to get 7 points across it, you end up seeing, okay, I need to have a 2.15 second cycle time if I'm including MS1 scans. The mass to charge range to cover. So I've kind of already talked to you guys about how I do 500 to 900, but hopefully walking out of this, if you want to cover 400 to 1,000, you'll see how to tweak the method. But in this case, I'm just saying I'm doing 500 to 900. You might want to change the mass to charge range covered. So one time I was doing a method where I had these PRTC standard peptides in there, and a lot of them fall below. So sometimes you might have really important peptides in a lower M over Z range that you want to cover, and then you'll need to shift your method a little bit. Next is choosing the isolation window width. So for a 500 to 900 M over Z method, generally my recommendation would be on a Q-Exactive or a Q-Exactive HF, I would use a 20 MZ wide isolation window. And on the Fusion, I would also use 20, but on a Fusion Lumos, I would use 10. And I'll explain why that is in a bit. So now just doing the math. So you need a cycle time of 2 seconds. You're covering a mass to charge range from 500 to 900 MZ, and your isolation width is 20 M over Z. So you can calculate how many MS scans you're going to have per cycle. That's your mass to charge range divided by the isolation window width. So that's 20 scans. And then you figure in each one of those cycles, I'm going to acquire a single MS scan. So on our instrumentation, it's about assuming 75 milliseconds for acquisition of that scan, right? So that means that your required MS acquisition rate to hit a 2-second cycle time is going to be 10.4 hertz. So for each individual scan, you have 96.25 milliseconds to acquire it. So does that make sense? Do people have questions on this? I know it's early for math. All right. So you're acquiring at 10.4 hertz, and from that knowledge, I think it drops out what your isolation width would be and what your AGC target should be. So this is a plot for the Q-Exactive HF. This is showing what is the acquisition rate of the instrument for MS scans versus the injection time of the instrument at various resolving powers. So at, for example, 30,000 resolving power, the instrument can acquire at a rate of about 14 hertz if it's doing a fill time of 20 milliseconds. Eventually, as you increase fill time, the acquisition rate slows down for any given resolving power. If you go to a lower resolving power, of course the instrument will scan faster. Higher resolving power, it scans slower. Can anybody tell me why does this curve plateau and then drop off? This one is kind of a more difficult question. So why would the instrument still scan at the same speed even though I'm increasing the inject time? What's that? Yeah. So it's, well, I saw you do this motion, which to me means Orbitrap. Yeah. No, I'm with you. So what it is you've got two things going on at once in the Q-Exactive, right? It's accumulating ions for the next scan as it does the mass analysis. So for a 30,000 resolving power scan, the instrument transient acquisition time, oh man, I just had to back calculate this. I think it's 64 milliseconds for that scan, right? So it requires about 64 milliseconds to measure the MS scan, and then once it gets past that, once your fill time gets far past that, it starts to impact the scan rate. If your fill time was 20 milliseconds, it doesn't matter if it's 20 or 25, as long as it's less than the amount of time for mass analysis, it's not going to impact the scan speed. It's almost like you can think of it as the limiting reagent in the reaction of acquiring a scan is the mass analysis in this realm, but then once you suddenly fill longer than the mass analysis is required, it starts to scale with the fill time. So remember I said that we want to scan at 10 hertz for our method, right? So if you draw a line here, this is 10 hertz. It kind of drops out. To acquire at 10 hertz, you're going to need a maximum fill time of about 65 milliseconds to acquire at that rate. If you set the fill time too high, you're going to run the risk of, if all of your scans hit maximum fill time, you might all of a sudden be acquiring at 8 hertz, and that's not quick enough. it should also be clear from this chart why we can't do 60,000 resolving power. Because we would be undersampling, we wouldn't be hitting our 10 hertz limit. So this makes a lot of sense on the QEHF, but the thing about the QEHF is I've been making all of these plots showing an instrument acquisition rate of 10 hertz. But the QEHF is actually capable of acquiring data at 20 hertz. Right? So that instrument can actually go all the way up here. So why do I not draw the line here? Why wouldn't I do a method with 4010M over Z windows? I'm going to give you guys a hint on YouTube. All right, let's see if I can make this work. So this is one of my favorite commercials, and this is what made me realize that on the QEHF I can't get away with actually scanning at 20 hertz for DIA.
How fast is it? Plenty fast, but it's not how fast you mow, it's how well you mow fast.
It's not how fast you mow, it's how well you mow fast.
It's not how fast you mow,
It's how well you mow fast.
So this commercial is actually about data independent acquisition. So what these wonderful men and women are trying to tell us is it's not how fast you acquire spectra, it's how well you acquire spectra fast. So you could scan on the QEHF at 20 hertz. The problem is those are going to be kind of crummy spectra. Okay, so that's your hint. So now, why would the spectra be crummy if I'm scanning at 20 hertz? There is lower resolving power. That's one reason. What's the other reason? What was that? I think you muttered it. You may have said it. Yeah, fill time. So you only have 17 milliseconds to fill the trap if you're trying to scan at 20 hertz. And that's actually not enough time to fill the orbit trap and actually hit your AGC target of 1 million ions. So we tested this out. So this is data showing the number of ions that are actually making it into the orbit trap when doing the method that has that maximum fill of 17 milliseconds and is scanning with 4010M over Z windows, okay? And this is the method with the 20MZ windows. So for the method with 20MZ windows, you have worse selectivity, but you have more ion counts. So you're managing to fill the trap, you're hitting your AGC target with 1 million ions, whereas you're underfilling by roughly half for that faster scanning method. So it's not how fast you mow, it's how well you mow fast. Okay, so now I'm going to jump into, I'm going to show you guys how to actually put together this instrument method on our instrument computer, which someone is currently acquiring data on, so hopefully they're not using it right now. Okay. Oh, we can't let our Dell support expire. Oh. Can you guys see this? Oh, yeah, okay. All right. So how many people are familiar with the Q-Exactive method editor? How many people have Q-Exactives? Okay, good. So this is good. All right. So the first thing I'm going to do when I'm creating a method is I'll boot up Skyline. And I want Skyline to generate that acquisition list for me. So we've already been through this, but it's in this settings, transition settings, full scan. And since I see some people furiously writing stuff down, I'll also mention that this is all in this publication, if you guys want to look at that too. And also you can always just email me. Okay, so the first step is to generate a isolation window cycle. So in Skyline, I think we know how to do this by now, but you can go down here and you click Add to create your isolation scheme. I'm going to do a 20MZ window DIA method. And in this case, I'll do 500 to 900 M over Z with 20MZ wide windows. And then I'm going to click this optimize window placement, and we'll talk about actually how that optimization works in a bit. Okay, so now Skyline's defined kind of the set of isolation windows for us, and obviously the next step is to actually plug this into the editor. So I'll hit OK, And now I'm going to purposely make a mistake so you guys can see this little tripping point. If you try to then hit File, Export, Isolation Window, Isolation List, that's telling Skyline to isolate the windows for you. For a Q-Exactive, it's going to say, okay, the product mass analyzer is not set to Orbitrap. So that's a common thing that I tend to trip over. The way you can change that is you just go in Settings, Transition Settings, tell Skyline here that it's an Orbitrap. I know that's actually going to change very shortly, where you can still export the method even if you have Centroid selected. But you have to select Orbitrap, hit OK, and then File, Export, Isolation List, hit OK. Oh, I guess it's thinking about it. Okay, and then you can generate the list. So we'll just go ahead and put that on the desktop. Okay, so the isolation list it exported is pretty simple. It's just a list of the windows, and they're non. Oh, that's really not rendering well, is it? It's just the list of the isolation windows. So then you can go to the Q-Exactive and start to populate the scans, if this will maximize for me. Guess I'll just do this. Oh man, I wish this was easier to read. Unfortunately, I don't really want to change the resolution on the computer because it's actually acquiring data, and I don't trust Windows to do that without screwing up. So I'll just have to read out kind of what I'm doing and make sure to tell you guys. Sorry about that. So the first step that I do in making this method is now we've in Skyline defined the isolation list we want to cover. The first thing I actually do is put in an MS1 scan. So I just drag the full a scan event, it's called full ms-sim, over onto the method. And in this full ms-sim scan, we set some of the properties. So I would usually set the resolving power to 60,000 for the scan. The AGC target, I'll put it at 1e to the 6. Maximum inject time for that scan, generally it's going to fill in 20 milliseconds, so it doesn't really matter what I put here, but I'll put 50. And for the scan range, I usually set it to the same thing with a little bit of slop of what I'm covering in the DIA run, so 495 to 905. So the DIA method is going to cover 500 to 900. This is that MS1 scan that we can get a little bit more added confidence in our detections from. Okay, and then the next step is to drag over the actual DIA scan. So we can use, let's see, what version of the editor is this? Okay, this is the one that has just DIA scan. So you can just drag a DIA scan event over in this editor. And then this is the part where we now import the actual isolation list from Skyline. So you define it as an inclusion list. So if you go to global lists and click inclusion, this is the part of the editor. You could just type in the master charge if you want, but you can also import it from Skyline. So I just hit File, Import, find that isolation list that Skyline exported, and hit Open. And now it's populated that list in the method editor. Now the next few things to do is actually I need to set this to advanced mode. So we have to tell the instrument that we're advanced, so it lets us change the spectrum data type to centroiding down here. So this is changing that to centroid. Try that one more time. All right. There we go. For the collision energy, I mean, different labs will have different optimal settings. I'll just leave this here. Well, change it to normal collision energy. For the isolation window width, we're going to do 20. This one here is really important, so I know it's very hard to read. This setting is the loop count setting. Are people familiar with what the loop count setting is in the Q-Exactive? Can someone explain it?
How many times does it go over that isolation?
Yeah. So what should I set the loop count to? Yeah, that's right. So you want to set the loop count to the number of isolation windows you have in the list. So in this case, I'm going to set it to 20. And then for the AGC target for this, you wanted to set it as high as you can get it without having to worry about space charging. So on the Q-Exactive series, I typically set that to 1 million. Maximum IT, you can set it to auto, which just means that it's going to try to kind of synchronize your maximum inject time to roughly equal the amount of time it takes to acquire the transient, to acquire the MS, to do the mass analysis. I'm actually going to enter it manually, so remember I showed you guys the chart, and we found 65 milliseconds, so that's where you put this in. And then the resolution is going to be fixed at 30,000. So, we could try to go faster at 15,000 and have narrower windows, but we wouldn't be able to fill the orbit traps, so we're not going to do that. This part says default charge state. So this is a pretty important setting. So this I'm setting to 2. Can anybody think about like a problem with that? Like we're just telling it to acquire those DIA scans at a default charge state of 2. How would that differ in terms of quality of spectra? If I'm assuming a default charge state of 2.
Well, this would apply a lower collision energy if
Yeah.
like so if you tell it it's a 1, it'll apply more, but anything over 1, it scales it down for a multiple time.
That's right. So the collision energy isn't necessarily going to be optimal for every peptide that's isolated in that window, right? So you've told it isolate everything in this window of roughly mass to charge at the center of the window, but assume everything in there is doubly charged. So some things might be underfragmented, some things might be overfragmented. That's just I don't see a way around that really. For DIA, you're always co-isolating multiple peptides. With DDA, you know what the precursor is when you isolate it, and you've determined the charge state, so you can optimize the fragmentation. Similarly, with SRM or PRM, you are going to know the charge state ahead of time. We don't have that advantage with DIA, so unfortunately we can't set the collision energy to be optimal for everything. Let's see if I forgot anything. No, that's pretty much it. So that's the simple, kind of straightforward method on the instrument. I mean, one major gotcha is right now this is showing like a 10-minute method. Just make sure that, when you actually put in your LC settings and set the actual runtime of the entire method, you might change it at some point. Yeah. Yeah.
I'm not super familiar with this chemical mechanics, I'm not sure. But we could do that also the scan range of the MS perspective.
Yeah. So I see what you're saying. So you're saying depending on the isolation, you're saying what's the scan range of the fragment ions that you measure set to. So I know on the fusion series, which I've been using recently, you can actually define that. So I actually set it. But yes, I believe that for a DIA method, it's going to alter the first mass to charge based on what you're isolating. And in fact, you can see, well, you can't really read it at all. Sorry about that. But there's this fixed first mass setting where you can actually define what you want to be the lowest mass to charge that it measures. So you can explicitly define that. But it will kind of scoot it along the range when you acquire it. I suppose so. Honestly, it's not really something I've optimized. On the Fusion series, I usually just plug in like 150 to 2000. But I think like there's no reason on the Orbitrap to not have it scanning the full range. I mean, unless you're trying to go really high mass to charge, then it would actually alter the scan, or it would alter some of the lenses for optimal transmission of those higher M over Z species. But I think like for DIA, generally you want to scan everything. I don't see why they would have it be narrower. In fact, I think it's... Yeah, and so it'll change your file size. I mean, I think some of it could be back from like the linear ion trap days. Maybe it's just habit. Like I don't I don't know why they would do it otherwise, but.
I mean, that's what I heard, that people can't do discrete at the close length, and then it
Oh yeah, then it goes higher. Yeah, that's what the Brogue does. I know that. I know that's what they started doing. So that's actually on the instrument series. Yeah, you can use 3 and then alter your normalized collision energy to try to get it to scan higher. Yeah. Okay. So that's basically the simplest kind of QEHF method. It's still not exactly what we do in the lab. So there's a little tweak that we do in the lab that I want to take you guys through now. Alright, so bear with me while I jump through here. Okay. So we've already said we can't really jump down to doing 10M over Z wide isolation windows, right? So imagine this case, though, with the 20MZ windows that I've talked about a lot, where you have the precursor of interest being co-fragmented with another precursor. It's just like in the slides that I showed. If you were acquiring at 10M over Z, you might resolve these two precursors, right? So they would be in different isolation windows and they wouldn't cause problems for you. But I've already kind of detailed why we can't drop down to 10M over Z or even narrower isolation. So what can we do? What we actually do in the lab is we overlap these isolation windows. So what this is showing is sort of a standard 20MZ method. It's zoomed in to just the end of each cycle, so just showing 820 to 900 in this case. And I've highlighted each cycle of scans as alternating colors. So what we do is we shift every other cycle over by half of the window width. So why would I bother to do this? Anyone want to explain it? Why is this guy spiky? That's right. Yeah. So what's happening is I haven't changed the number of how frequently I scan any given peak. But imagine I plug into Skyline and I say, okay, I want to extract the fragment ions for this particular precursor here. So Skyline's going to then extract from the scans that are outlined in white. It's going to extract from the blue, the red, and the blue. And the two things are only co-isolated now in the blue scan events, right? So in the blue scan, you see the interference still, but in the red scan, you don't see it. And then in the blue, you see it, and so on and so forth. So it takes on this sort of sawtooth pattern. And you can actually mathematically demultiplex these spectra. So you can imagine just looking at this and saying, oh, this is sawtooth, and just like delete the transition. But we can actually do better about this. It's actually a linear system of equations that I'm not going to get into the math, but you can do a non-negative least squares solve to basically narrow down to just a 10MZ isolation window. So what's really cool about this method is all you've done is you've shifted one thing over by 10M over Z. You haven't impacted your cycle time. You're still covering 500, 900 M over Z. You're still hitting the peak every 2 seconds, but you basically doubled your precursor selectivity for free. And here's proof. So here's isolated transitions for this long peptide. Here's what the fragment ion traces look like for a 20 M over Z wide isolation window. This is dropping down, so this is when you overlap them. So this is a real example of that sawtooth pattern. So now what you can see is that these things that are there in 20, once you overlap, it becomes pretty clear that all of these fragment ions are coming from a species that's outside of the 10M over Z isolation that this peptide falls in. And then when you demultiplex the data, so this is applying the computational approach, which Skyline does. The algorithm's implemented directly in Skyline, and Austin actually also implemented it in MS Convert from ProteoWizard. You'll actually end up with spectra that looks like this. And then the next question is, well, how does that compare to had you actually isolated with a 10M over Z window? And it compares pretty well. It looks extremely similar to if you had acquired with an actual 10M over Z window. So we're getting close to having 10M over Z data quality using 20MZ windows just by doing this overlapped isolation. Are there any questions on that? So one thing that's kind of key to this method is the uniformity of the isolation quad. So this is a question that people generally ask a lot about DIA methods is, I kind of mentioned this issue of what happens at the edges of your isolation windows. So in DIA, remember, you're not always isolating right in the center of the window. So this is a plot actually showing how flat is the quadruple isolation on the Q-Exactive Plus, or HF series, with the segmented quad. So what this is showing is basically, if I isolate an ion right in the center, it isolates with efficiency normalized to 1, and it only really drops off when you start to get to the edge here. So I would consider this very good isolation efficiency. On a Q-Exactive, it's going to tend to kind of drop off a little. So having this flat isolation efficiency is really helpful when you're doing the overlapping window approach in particular, because in every other scan, the peptide's going to get isolated, say, here in one and then here in the other. So we need that flat isolation efficiency. So how much does this overlap demultiplexing help? This is showing the lower limit of quantification. So this is doing DIA with these 20 MZ wide windows. We had an average lower limit of quant of 4.8, and we roughly doubled our sensitivity when we went to this overlapped approach. So that's why we do this. I'm going to skip through this. So I want to show you guys how to actually modify the method and create an overlapping window method in Skyline. So I'm going to do it on the local computer here since the other one is rendering poorly. So what you do is you go to settings, transition settings, just the same. We're just going to make a slight tweak to the acquisition method. So I'm going to do DIA, Orbi, click add, and do 20 MZ overlap. So in this case, it's still the same process. You're setting pre-specified isolation windows, and you hit calculate. And again, covering 500 to 900 MZ. 20 MZ wide windows, optimize placement, but I'm going to set deconvolution to overlap. And when you do that, it's actually generated this method with the overlapping windows. So Skyline is kind of showing us that with these plots, it kind of makes it clearer that the two windows overlap each other. So unlike before where you had red and that kind of is scary and means an error, the blue is just there to make it clear that these windows, in fact, are overlapping with each other. It's not indicative of a problem. So at this point now, Skyline will export a transition list or an isolation list with this method. Oh, whoops. Single. Right. So we'll set both to Orbitrap, export isolation lists. Okay, so here's what the isolation list looks like. This is just the first cycle here, so the first cycle is going to be 20 scans. And then after that, you can, 21 actually. And then after that, it repeats and it's got the second cycle offset. So one key thing for this is when you're doing these overlapping approaches, make sure that you don't sort the isolation window list, because then it's actually not going to work. So that's a very common problem, because then when you've done that, you could still demultiplex the data, but then you've then reduced your sampling time for any given peak down from 2 seconds to 4. So make sure that this method is applicable for, I think, any instrument that can do DIA. So make sure your method editor doesn't sort this for you. I think an earlier version of the QE, very early, probably no one even has it anymore, used to sort it at one point, and you just have to be careful that it doesn't. So this is the actual method that we use in the lab. So we use 20MZ overlapping windows for our QEHF. But there's one little tweak that you have to make when you use this overlapping window list, which is actually on the QE you don't have to change it, so I take that back. You can just plug in this isolation list here like I did before. You click inclusion and set the list, and then your loop count, you set it to 20, and it'll still acquire the MS1 every other scan. So then once you've acquired that data, in Skyline, so long as you have your transition settings set to this overlapping scheme, you can go and import that raw data, and it's going to do the computational demultiplexing on the fly. So you don't need to worry about any of that. If you're doing a lot of these acquisitions with a lot of these raw files, I would actually recommend that you use the MS Convert implementation that Austin wrote. It works a lot faster. It takes about 20 minutes a file, right? 15 minutes per file. It used to be faster. But then we just slow it down to make it more practical, I guess. But anyway, that's actually the approach that we do in the lab. So does anybody have any questions on that method before I get into some more details? Does that make sense? Can people go home and do this?
About the loop count?
Yeah.
So if you had 21 and 20
Yeah, it should be 21. I took a shortcut there. It should be 21.
for both?
Yes.
Oh, so
Well,
both, because one is 20 and the other one is...
oh, okay, yeah. So let me...
So how do you deal with the MS1 scan?
Yeah, so, sorry, I was kind of lazy in my explanation there. Alright, so when we tell Skyline to do this 500 to 900 M over Z thing, it actually ends up writing out an isolation list that's... It's actually 21 scans in each of these cycles. Okay, so the reason it does that is when you're doing this sort of overlapping thing, you do lose a little bit of M over Z range because you've got this little kind of overhang here where stuff's only half sampled. So Skyline says, well, I need to fully sample everything that in the range that the user asked for. So it's going to tack on this little extra window because we're losing that part. So that's going to be a 21 scan cycle, and the loop count should be set to 21 if you're using the overlap. But if you're not, set it to 20, because if you weren't doing overlap, it would just output a list of 20 windows. Any other questions?
Do you know if you can do this on a 5600?
You should, yeah. Yeah, I think you should be able to, and Skyline should demultiplex it.
Try to do it. Again, nothing, Brendan always says nothing works until someone's tried it.
Yeah, no, I totally think you should be doing this on a 5600. Yeah. Yeah, and please, yeah, make sure in the method editor that it's not like sorting the isolation windows for you. Any other questions? Okay, cool. So now I want to kind of explain how Skyline does this sort of optimization of the window edges and their locations. Okay, so we talked about this issue in DIA data where the isolation window is not necessarily centered on your precursor of interest in DIA. So this is kind of trying to indicate if this is a particular MS1 scan, this is showing a peptide precursor that we might be interested in. And I'm just showing the theoretical worst case scenario where if you imagine in your DIA method that these are two isolation windows, your precursor of interest falls right in the junction between those two windows, right? And so that's something we would like to avoid to whatever extent possible. So there's a couple ways around this problem. The one I'm going to show you is just saying, well, I'm going to try to optimize where these edges are to avoid this case. The other way to do it is just to add some slop. So just to put margins on the window, which is going to say, well, I'm going to let these windows overlap a little bit, so I'm going to make this window come out to here and this other one come out to here. To optimize the location of the windows, it's all based on this observation about peptides, which is they're all made from hydrogen, carbon, oxygen. All of the elements they're made from have a similar mass, right? And the key is that their mass excess is all 0 or about 1. It's just a roundabout way of saying is they're roughly integer masses. So you're building peptides from these building blocks that all have these almost kind of quantized potential masses. So this is a plot that shows fragment ion mass to charge versus prevalence of fragment ions. So this is if I took, theoretically, I took, say, all of the peptides that I've ever detected, I think this is in worm, and I said, what are the fragment ion mass to charges of the Y ion series for all of them? And this is showing what the histogram, what the distribution is of occurrence of those masses. So what you can see is that there's this spacing, and it's because you're basically building all of your peptides with something like Lego blocks, right? So if I'm trying to build a peptide, and it's like a Lego tower, I can't build a peptide that's 1.5 Legos tall. I can only build one that's 1 or 2. And that's the same thing with the peptides being made from things with these kind of unit mass values. So you end up realizing that you have this sort of distribution, and if you start to think about precursors, like a doubly charged precursor, for example, that's when you get these sort of half masses in between, that are in between single jumps. But given that the peptides all sort of fall into this range, you can imagine that if you wanted to make like the world's worst DIA method, you would have all of the edges right where you know that you're going to have precursors, right? But if you want to make the best DIA method, you just simply have to scoop those windows a little bit, right? So the distance between these peaks is 1.00045475, roughly. And so when you tell Skyline, optimize my DIA isolation windows, what it's going to do is you say, well, I want the window to be 20 MZ wide. It's going to say, well, we're actually going to make it 20 times 1.00 blah, blah, blah. So it's going to make them that, and it's going to automatically shift them by the fixed offset that places it in those regions where you're not likely to see peptides. So figuring out that optimal offset between this is the worst method, has a given offset, and say I'm shifting it by now 0.1 m over z and it's optimal. This is a plot showing for given offsets of the windows ranging from 0 to 1, so moving those fence posts anywhere from 0 to 1. This is showing the prevalence of edges. How often does an edge fall on an actual peptide? And you can see here that it's very low, around this 0.2 region. So what this all goes to say is that if you set using this optimized window setting, if most of your analytes are kind of doubly or triply charged, you can mostly avoid having the windows actually isolating a peptide. Now, that's not to say that you shouldn't use margins at all. It's just this is kind of the best we can do without making the windows overlap to each other. Here's an example, actually, of what it would look like. So before I was showing you guys the QE plus isolation, this is showing where the isolation windows would be if you're using 4MZ windows and it's overlaid onto an MS spectrum. So you can kind of see that you still certainly have things near the edge of the windows. So it's not a perfect solution. And it's particularly a problem on the kind of QE classic series, where this is actually, what I did for this experiment is I measured the isolation uniformity by injecting the tune mix, and then I scanned a 4MZ window over the tune mix and looked at my signal for the calorant. And so then that's what you get. You get this sort of uneven plot. So keep that in mind when you're developing these methods. And what I can say is the quads on the Q-Exactive classic, and the Q-Exactive classic is going to look like this. The QEHF and QE plus is going to be much more flat. Any of the AB SciX instruments are going to be much more flat. They have really good quads. And the Fusion non-Lumos will be somewhere in between. Okay, so that's kind of where I want to conclude. If anybody has any questions, if people don't, I can go into one more little thing that's really complicated.
One quick question about is there any benefits in constant isolation using those factors compared to the variables like the science that anybody could do it?
Oh yeah, so you can definitely do it. So So yes, I can see a theoretical reason for doing that. We haven't directly tested in our lab. Have you guys? You guys have. So maybe you ought to speak on it a little bit about what sort of improvements you see. So to put people on the same page is really fast. I just wanted to show them this plot. Like this is what the variable width scheme would look like. What it's doing is it's saying I'm going to use narrower isolation windows. Oh man, that doesn't work well, does it? It's saying I'm going to use narrower isolation windows in the peptide-rich regions, in the peptide-dense regions of mass to charge. Oh man, struggling here. And then at the higher mass to charge, use wider isolation windows. Yeah.
Yeah, and my feeling is that the benefit of having more windows than compared to being very reliable. So I think the variable will improve it a little bit, but I think it's much better to make more windows.
So if you wanted to try the sort of variable isolation window thing, these methods are built into Skyline on the default install. So you have these, I think the first one is the swath 25, right? That's the 32 window one. Yeah, and then the variable window approach is the 64 one. So if you actually look at the isolation width, you can see the window range, the window width is varying over time. The difficult thing is, I don't know the specifics of implementing it on the SciEx instrument, but if you're implementing it on the Q-Exactive series, it is still doable, but you can't do it all in a single DIA scan event. You need to make a separate DIA scan event for every single window. So I can bring it up. So before we had this one DIA scan event, the problem is you set in that DIA scan event your isolation window here as 20 MZ, and you can't, in the QE series, make the width variable for different scans, so you would actually have to do something like dragging another scan event over in for each window, so you would have 64 DIA scan events. On the Fusion series, I believe you can actually enter the isolation window width in the list. Yeah, no, thanks for bringing that up. That's a common approach to do this sort of variable window thing. It's worth trying.
I'm wondering whether it's possible to adjust the collision energy for MOVZ windows. Would there be any benefit?
There is, and in fact, the instrumentation already does that. So at least for the thermo step, it actually optimizes. It has a built-in optimization, so it's actually affecting the collision energy based on where the window is located.
If you have a preset
charge state, but it also, it says, so it has these like multiple curves, right, of M over Z versus the actual collision energy that's applied. So imagine a curve like MZ versus collision, and then it has a separate curve for each charge state. So when you're setting a default charge state of 2, it's...
So you pick in a method here charge state 2, and that's what's going to be the default charge state.
For charge state, yes.
It doesn't isolate only tertiary 3.
And it's going to calculate the collision energy based on that charge state.
Right, so it does. It calculates the collision energy based on the fact that it's doubly charged, and it also affects the collision energy based on where the window is, right? So if it's a higher window, it will do the higher collision energy. But of course, it can't simultaneously optimize for multiple charge states. Yeah. So yeah, I guess the best we can do is to say, okay, well, most of the things I care about are going to be doubly or maybe triply. And it'll optimize assuming that, and then also it will do a slight optimization based on where the window is located. Okay, any other questions? All right, I'll stop there then. I think it's about perfect timing, so it's time to break for lunch. Thanks.